and byte array objects. Memory views. Memory view objects allow Python code to access the internal data of an object that supports the buffer protocol without copying. Class memory view object. Create a memory view that references object. Object must support the buffer protocol. Built-in objects that support the buffer protocol includes bytes and byte array. A memory view has the notation of an element, which is the atomic memory unit handled by the originating object. For many simple types such as bytes and byte array, an element is a single byte, but other types such as array.array may have bigger elements. Length of view is equal to the length of toList, which is the nested list representation of the view. If view.endDem is equal to 1, this is equal to the number of elements in the view. Changed in version 3.2. If view.endDem is equal to 0, length of view now raises type error instead of returning 1. The item size attribute will give you the number of bytes in a single element. A memory view supports slicing and indexing to expose its data. One-dimensional slicing will result in a subview. For example, let's do the example in the IDE. So this is view, memory view, bytes A, B, C, D, C, E, F, G, and then try to print V1. Print V1. So it will print byte A, 98, correct, and V minus 1, so it will print subscript minus 1. It will print ASCII code for Z, that is 103 98 99 900, okay, 10, and then V1 to 4 slice V1 to 4. This will give you memory location, and bytes 1 to 4 will give you value of it, BCE, right? So if format is one of the native format specifiers from the struct module, indexing with an integer or a tuple of integers is also supported and returns a single element with the correct type. One-dimensional memory views can be indexed with an integer or a non-one integer tuple. Multi-dimensional memory views can be indexed with tuples of exactly n-dim integers, where n-dim is the number of dimensions. Zero-dimensional memory views can be indexed with the empty tuple. Here is an example with a non-byte format. Import array. Import a is equal to array.array. This one is all. Memory view A. Print M0. Print M0. So let's see. Minus 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 1, and then M minus 1, M minus 1, 4 4 4 4 4, and M colon 2 dot to list, M colon 2. So this one, then this one, right? This one and this one, 2 elements, correct? If the underlying object is writable, the memory view supports one-dimensional sign assignment. Resizing is not allowed. For example, data byte array, memory view, read only. let's try with this. Print v dot read only, is it true or false? False. Correct. This one is assignment. Ordinal bz, z, v0 replace it with z, and print data. Print data, and here we will see z instead of a. Okay, and then v1 to 4 is equal to byte 1 to 3, print data. So 1 to 4, this is 1 2 3 4, 4 is excluded, so BCE will be replaced by 1 to 3. BCE is replaced by 1 to 3. Now 2 to 3 sperm, print data. So here 2 to 3 means 2 3 is not included, but we have more values, so this will give value error, some error. Value error, memory view assignment, L value and R value have different structures. Correct. One dimensional memory views of hash table read only types with formats capital B, small b or C are also hashable. The hash is defined as hash m is equal to hash m dot 2 bytes. So let's do it. This is memory view for A, B, C, D, C, E, F, G. Hash V is equal to that. So print hash of V. Both should be equal, right? True. And hash of V24 is equal to hash of CE. Hash of V24 0, 1, 2, 3 should be CE, right? True. Hash of V minus 2 should be ABCD minus 2. Correct. Hash of V minus 2, so minus 1 minus 3, this should be true. Correct. Changed in version 3.3, one dimensional memory views can now be sliced. One dimensional memory views with formats B, capital B, B or C are now hashable. Changed in version 3.4, memory view is now registered automatically with collections.abc.sequence. Changed in version 3.5, memory views can now be indexed with tuple of integers. Memory view has several methods. Underscore underscore equal underscore underscore method exporter. A memory view and a PEP 3118 exporter are equal if their shapes are equivalent and if all corresponding values are equal when the operands respective format codecs are interpreted using struct syntax. For the subset of struct format strings currently supported by toList, V and W are equal if v.toList is equal to w.toList. Import array. Let's do the example. Import array. A is equal to array dot array I 1 2 3 4 5 array dot array D 1.0 C 53 or memory view X. Memory view of A is X, memory view of B is Y, and now print X is equal to A is equal to Y is equal to b. I think this should be true. Why? Values are correct. X is equal to 2 list is equal to a dot 2 list is equal to y dot 2 list is equal to y dot. This should be true. Z is equal to y, okay, is equal to c. Minus 2, so 5, then 3, and then 1. Okay, so this should be correct. True. Okay. If either format string is not supported by the struct module, then the objects will always compare as unequal, even if the format strings and buffer contents are identical. From C types, import big endian structure, comma C underscore long class BE point big endian structure fields is equal to X, comma C long, comma Y is equal to C long. So this is advanced programming. So let's print a is equal to point and print a is equal to b. Let's see, both are false. Note that as with floating point numbers, v is w does not imply v equal to w for memory view objects. Changed in version 3.3. Previous versions compare the raw memory disregarding the item format and the logical array structure.